So we were talking about the stresses at point H and how we can find the corresponding minimum and maximum stresses, principal stresses, and maximum shear. We'll see that point H is really a particular point because we have seen that for H, sigma x is 0, sigma y is 0, and we just have a shear stress tau xy. What is the particularity of this point? If you want to calculate the average stress for this point, it will be equal to half times 0 plus 0. So sigma average at H is 0. And for the radius corresponding to this point H, it is equal to radical also of 0 square plus tau xy square. So it's equal to tau xy. So if you want to represent, if you want the circle corresponding to point H, this circle is centered at the origin because sigma average, we know that the center of the circle in general has coordinate sigma average 0. So the center will be just at the origin. And this is a very particular case because in general, whenever we have the maximum shear stresses, they don't have they don't have to have sigma x and sigma y 0. Because if you remember in the course material, we have seen in general that for we can have a circle, let's say, this is an example. If sigma average is different than 0, we can draw the corresponding circle. And tau max will be here. It will be equal to the radius, and tau max will correspond to sigma average. So in general, maximum shear does not have to correspond to 0 normal stress. But this is a very particular case because in this case, the maximum shear stress is taking place for 0 normal stress, okay, which is in general not the case because in general, the plane corresponding to maximum shear correspond to a certain value of sigma equal to sigma average. But because here sigma average is equal to 0, this is a particular case where in plane of maximum shear, the normal stress is sigma x sigma y is equal to 0. And now we'll see together when I introduce for you the Mohr circle, we'll understand that this point will represent sigma x and minus tau xy. Sorry, sigma y and minus and plus tau xy. And this point will represent axis x. And we'll understand this when we introduce Mohr circle. So this is sigma x and minus tau xy. And here in particular, sigma x, sigma y 0. So the 2 points representing, if you want the axis xy here are 0 plus tau xy and 0 minus tau xy. And concerning the points of principal stresses, these are the 2 points of principal stresses. And it's clear from the figures that sigma maximum is equal to the radius and sigma minimum principal is equal to minus the radius. Because if you apply here for sigma average equal to 0, you get sigma max equal plus r, sigma minimum equal minus r, and tau max equal r. So this is a particular case presented by this circle where you have maximum shear correspond to normal stress 0. And you have principal stresses just equal to plus r and minus r. Okay, and now this will introduce us to the new section of this course, which is the Mohr circle. Okay, so now we'll see in detail how to draw the Mohr circle and how it can help us into characterizing the state of stress in any direction of interest, not only axis of maximum shear and axis of maximum normal stress. Okay, so going back now to the course material, as we said, we will go over how to draw the Mohr circle and how it can help us into getting the state of stress in any direction we want. So until now, we have considered 2D stresses, and we said that we can determine, once we know the state of stress in one frame XY, we can deduce the minimum and the maximum principal stresses, and we can deduce the maximum shear. Now, what about any other direction? If you are interested into getting state of stress in any other direction relative to XY, what we should do is the following. So the circle of Mohr is a circle used to calculate the stress of state of an element at any orientation if we know the state of stress in frame XY. So we are still dealing with 2D plane stress. Let's say I was able to identify in a plane XY what is sigma x, what is sigma y, what is tau xy, and I want to deduce what is the state of stress in any other orientation. And if I want, for the same element, if I want to deal with an axis, let's say, doing x prime, y prime, doing an angle of theta with x, how can I deduce the state of stress for these axes? So the idea is the following. According to the formulas we developed before, you were able to relate sigma x prime, sigma y prime to the state of stress with theta. But instead of dealing with formulas, we can use geometrical method. And this geometrical method is based on the Mohr circle. What is the idea of the Mohr circle? Once I know the state of stress in frame XY, I can draw a circle which will represent all possible state of stresses. This is called the Mohr circle. How I construct this circle? I just have to put 2 points. One point is of coordinates sigma x minus tau xy, and the other point is of coordinates sigma y plus tau xy. Once I put these 2 points, then I can construct my circle, because you know these 2 points are opposite to each other, because we have seen, if you remember, we have seen together that if you rotate an angle theta here on the circle you construct, you turn an angle 2 theta. So between x and y, the angle is 90. This means on Mohr circles, the angle will be 180. So any 2 perpendicular axes would be represented on Mohr circle by a diameter of the circle, and this line will be centered on at point C, which is the center of circle, which will lie on sigma axis, because from definition we said we take point X of coordinate plus sigma x minus tau xy. You will tell me why for sigma x, for point X, I take sigma x minus tau xy, and for point Y, I take sigma y plus tau xy. It's very simple, because from my derivation, whenever, if you remember, I found the angle between the principal axis and axis x and y, I found that this angle is given by the following: tan 2 theta p is 2 tau xy over sigma x minus sigma y. So let us take the case, and it will always work. And just to demonstrate for you why we are taking this here. If you take, let's say, sigma x larger than sigma y, and you have tau xy positive, okay? In this case, if you replace in this formula, you should rotate, so this is positive, and sigma x is larger than sigma y, this is positive. Your angle 2 theta p should be in the counterclockwise direction. So you should rotate from x-axis to the principal axis along the counterclockwise direction. And we have seen together here, if you want to draw the rotation, if I consider x-axis, and to be able to rotate from x-axis to the principal axis here, in the counterclockwise direction, point X should be below the axis. So it should be characterized by a negative coordinate. This is why we take for X, sigma X minus tau XY, and for Y, sigma Y plus tau XY, because this will lead to a positive angle of rotation from X towards sigma maximum. Okay, of course it will work for any combination. Yani not always tau XY will be positive and sigma X higher than sigma 1. Whatever is the combination you try, you will see that I should take for X coordinate sigma X minus tau XY, and for point Y coordinate sigma Y plus tau XY to give me the result, this result, that tan 2 theta P is equal to 2 tau XY over sigma X minus sigma Y. Okay, so the rule will be, once I determine the state of stress, sigma X, sigma Y, tau XY, I can represent the Mohr circle by just putting 2 points, X of coordinate sigma X minus tau XY, point Y corresponding to Y orientation of coordinate sigma Y plus tau XY. I relate the 2 points. The intersection with sigma axis will give me the center. And of course, the coordinates of center will be sigma average equals sigma X plus sigma Y over 2. And it will be on sigma axis. So of course, for the center, tau is 0. So tau C is 0, while sigma C is sigma average. And now I can construct the circle. Once you construct the circle, you can identify the principal axis. You have point A correspond to sigma maximum 0, because we have seen that always for the principal axis, the shear is 0. And sigma max is given by sigma average plus the radius. You can see this from the circle. And point B correspond to sigma minimum 0. And sigma minimum is simply sigma average minus radius. Now, if you look at the maximum shear stresses, you don't have, for maximum shear stress, you can have normal stress, unless we have the particular case we have seen together in the previous problem. So here in general, maximum shear correspond to these 2 points of coordinates sigma average plus radius and sigma average minus radius. And from this circle, you can deduce geometrically for any orientation. Okay, so let's say I told you we rotate from x-axis in angle alpha. What will be the state of stress? You say then, if I go to Mohr circle, when I rotate alpha on the figure, I should rotate 2 alpha on the Mohr circle. Okay, because if you remember from derivations we did before here, when we derived the circle together expression, okay, here you have cosine and sine of 2 theta. So when you draw the circle, rotation in the circle from one orientation to the other, if you rotate theta on the element, you should rotate 2 theta on the circle. Okay, so now going back to your Mohr circle, when I tell you if I rotate relative to x in angle of 40, let's say 50 degrees, then you say I should rotate with respect to x here in angle of 100 degrees. And then the new state will correspond to these 2 points, this one and this one. And this point, let's say I call this x prime and this is y prime. This point will represent as coordinate sigma x prime minus tau x prime y prime. And this point here will represent sigma y prime plus tau x prime y prime. And geometrically, from simple geometrical analysis that we'll do together in problems, you can find what is sigma x prime, what is tau x prime y prime, what is sigma y prime, and then you can define the state of stress relative to any orientation you want using geometrical properties in Morse circle. Now, so as we said, with Morse circle uniquely defined, the state of stress at other axis orientations can be computed. And for the state of stress at an angle theta, here, for example, if you rotate clockwise an angle theta with respect to xy, then on a Morse circle, you should rotate an angle of 2 theta clockwise in order to get the state of stress in x prime, y prime. And if you rotate from x in counterclockwise direction towards x prime, y prime, then you should rotate on Morse circle 2 theta into the counterclockwise direction. Okay, and of course, as we mentioned, for the new points, the coordinates of x prime will be sigma x prime minus tau x prime y prime, and y prime sigma y prime plus tau x prime y. Now, you have several particular cases that we can represent in Morse circle. The first particular case is the case of centric axial load. So let us consider the following element. This element is subjected to normal stresses under the effect of T and T prime. So if I take in particular this element here, and I want to study the state of stress along this element, I can say that I only have normal stress created by force P. And this normal stress can be calculated if I do any section here. I have sigma x equal P over A. And since I only have axial load along this, for this space, I just have a normal stress. I don't have bending moment. I don't have torsion. So I can say then that I only have sigma along axial direction. So for this state, I have sigma x equal P over A and sigma y tau xy equal to 0. If I want to represent this state of stress on Morse circle, I just have to put my 2 points. My first point is of coordinates sigma x minus tau xy. And because tau xy is 0, so the first point will be sigma x 0, and it will be located here. This is my point x representing x axis, stress, state of stress. And the second point is sigma y, also 0, because tau is 0. And since sigma y is also 0, so my second point is the origin of axis sigma and tau. So now if I draw this circle, I can see this is also a particular case. If I draw this circle, I can find that the principal axis are x and y. Yani already x and y represent the principal axis because they are characterized by 0 shear. And if I want to deduce the axis of maximum shear stress, as you can see in this figure, the axis of maximum shear stress will be centered. They will have sigma average, and they will have as coordinate plus radius and minus r. So tau, I can say that tau maximum is equal to the radius of the circle. And the radius of the circle is sigma x over 2. So tau max is P over 2a. And for this case, for this plane of maximum shear, sigma is equal to sigma average equals to sigma x plus sigma y over 2 equal also to P over 2a. So the maximum shear will be equal to the normal stress in the plane of maximum shear, equal P over 2A. And if I want to represent this this frame x prime, so if you want, this is x prime and this is y prime. One second. If you want to be accurate, okay, we have that this point, so this point D correspond to coordinates sigma prime and plus tau max. And this point E will represent coordinates sigma prime minus tau max. And if you want to represent these axes on your figure, okay, so this is x-axis. This is my x-axis. This is my y-axis. Since I rotated on Mohr circle from big X, point big X to point big D, an angle of 90 degrees, this means that I should rotate on my element an angle of 90 over 2, which is 45 degrees. So this is axis small d. Okay, and of course I can say that since I rotated from big X to big E an angle of 270 degrees, so I should rotate 135 from X, 135 degrees to get axis small e. And as you can see, small d and small e will be perpendicular, of course, because big D and big E are collinear. So you have an angle of 180 degrees, are collinear with the center of the circle. From D to E, you rotate 180 degrees counterclockwise on Mohr circle. So from D to E on the element, you should rotate 90 degrees. And now if you want to represent your state of stress along the element, this element will have faces perpendicular to D and E. And if you want to represent the state of stress, you have sigma prime along D equal to sigma prime along E. You have a tension stress at these faces. And the value of sigma prime is P over 2A. Now concerning tau, as I told you, since you have here at point D a positive, a coordinate of shear positive, this means that tau, this represents minus tau d e, minus tau dE. This means that the shear stress, okay, on this face should be negative. And you can see this because if I want to represent it, okay, if I want to represent a negative shear on this face, I will put it like this, because sigma d is unit vector perpendicular to this face is along positive d, and because from Mohr circle the stress at d is negative, this means that the shear should be along minus e. So this is tau max presented on this face. It should be downward, and then I can deduce the direction of shear on all faces. Okay, so in this case, I have along this face negative shear, tau d. Okay, and this is how I can represent the state of stress at maximum, in plane of maximum shear, for this particular case of centric axial loading. And I can deduce the state of stress at any orientation from xy So if I just tell you what is the state of stress along these two axes, x prime, y prime, knowing that the angle alpha of rotation here is 30 degrees, for example, you tell me if I rotate 30 degrees on this element, I should rotate 60 on more circle, 60 degrees. And this will represent big x prime point. This will represent big y prime point. And the coordinate of this point will be sigma big X prime minus tau big X prime y prime. And geometrically, if you look at this figure, for example, what is sigma X prime? Sigma X prime is, if you project here, this is sigma X prime. This is sigma of X prime. How you get it geometrically? It's equal to the radius of this circle, r, plus this distance, which is r cosine 60. So this is how geometrically you can find what is sigma X prime. And for y prime here, okay, also you do projection. You say that sigma y prime is equal to this distance, which is the radius, minus this distance. This distance is r cosine, this angle is 30. So sigma y prime is r minus r cosine 30. And if you want to find tau x prime y prime, you say that this represents minus tau x prime y prime. So tau x prime y prime is negative, and tau x prime y prime is equal to minus this distance, which is r sine 60. And in this way, geometrically, you are able to determine the state of stress for any orientation. Okay. Now, another particular case is torsional loading, which is very, if you want, we'll get a circle similar to what we have seen in the last example. But here we just have torsion. In the previous example, we have superposition of torsion and shear effects, but both will lead to shear stress. And because the two shear stresses were collinear, so we got something very similar to the case here. So whenever you have a torsional loading, pure torsion, and you want to determine the state of stress at the free surface, we have discussed together that for free surface, we have a 2D plane stress. So if you consider this free surface and you want to represent the state of stress on it, we know that torsion will only lead to creation of, so if I take this phase from torsional moment direction, it will create along this side, it will create a value of tau equal to Tc over J. This is the formula from chapter 3, where T is the torsional moment, C is the distance from the axis of rotation to the side we are considering, and J is the polar moment of inertia. And then all you have to do is to represent for this element what are sigma x, sigma y, and tau. And of course, in pure torsion, no sigma. Sigma x equals sigma y equals 0. And we only have a shear due to torsion, and this shear at this phase, its tau xy is positive, because as you can see, it is, if I take the normal to this side, it's along positive x, and tau is oriented along positive y. So here tau xy is positive, equal to tau max equal to Tc over J. So the 2 points representing your state on the Mohr circle are big X of coordinates 0, which is sigma x, and minus tau xy. So we can, and tau xy is equal to Tc over J. So point X has coordinate 0 and minus Tc over J. So you can represent it by this point here. This is point big X. And point big Y is 0 plus tau xy. So this is point y, and this distance is TC over J. So now once you have big X, big Y, you can draw your circle. Your circle is centered at sigma average, which is here in particular 0, and you get this circle. And you can deduce easily that for this circle, you have that sigma principal stresses max and minimum are equal to the radius of the circle, and the radius of the circle is TC over J. So you can say that for this particular scenario, sigma max is plus TC over J, sigma minimum equals to minus TC over J, and tau max is all TC over J. So this is a particular case where the absolute value of the maximum shear and maximum normal and minimum stresses are equal. Now, let us start to practice with problems on using Mohr circle to get the state of stress in any orientation. So going back to our problems. You have the following now. Solve the previous problem we did together for the given state of stress to determine the normal and shearing stress after the element shown has been rotated through 25 degrees clockwise and 10 degrees counterclockwise. If you remember, we have already solved this problem using the formulas developed at the beginning of the course, okay? And before, we just solved using the formulas without taking into consideration the circle. The circle is of extreme help sometimes because you can easily use geometrical techniques to find stresses in any orientation, okay? Of course, you can use both methods. If they don't specify for you in the example, you are free to use the method you want. But if they told you use Mohr circles, then you should use geometrical techniques. If they told you use just so they can tell you develop the relation between shear stresses for any orientation, so you can go back to the derivations. Or if they don't ask for derivation, you can directly use the formula to calculate the corresponding stresses for any orientation. Here, I want you to use the Mohr circle, okay? So what we will do first, as usual, for this element, we consider the axis. So this is X, this is Y. We have first, we can see that along X, you have compression effects of 60 megapascal. This is why you have a negative sigma X. Sigma X is minus 60 megapascal. Along Y, you have tension. So sigma Y is plus 90. Now for tau xy, we can look at this arrow here. This is tau xy. You have that the normal vector is along positive x, and the shear vector is along positive y. So this is a positive tau xy. So tau xy is plus 30 megapascal. Now, once I determine this state of stress, all I have to do is to draw the Mohr circle. As we said, to plot the Mohr circle, we need 2 points. The first point is characterized by plus sigma x, which is minus 60, and minus tau xy, which is minus 30. And second point is characterized by plus sigma y and plus tau xy. So now we are ready to plot Mohr circle. We just put first big X, big Y. As we mentioned here, big X has negative sigma component, negative tau component, and big Y has positive sigma component, positive tau component. Once we put the 2 points, all we have to do is to relate them. The intersection with sigma axis will give us point C, which represents the center of the circle. And we can easily calculate sigma at C, which is sigma average, which is sigma x plus sigma y over 2. Now, here X and Y are not the principal axis, and we can deduce their orientation relative to the principal axis. Why we should do this? Because look, geometrically, when we do projections, we will project on this axis. So it's important to know what is the angle between XY axis and the sigma axis. And this angle, we know that this angle of rotation from X towards the axis of sigma is the angle 2 theta p. Okay, because we have that the angle which will allow us to go from XY orientation to principal axis orientation is on the Mohr circle is 2 theta principal, and on the element is theta principal. Okay, now as you can see in this figure, when we go from big X to axis of sigma, we are moving into the clockwise direction. So it's a negative angle. Or if you don't want to put plus and minus, you should put the direction when you calculate. And here, how to calculate this angle? It's very simple. If you look at the figure, to get this angle, you can write that tan of 2 theta p is equal to this distance, which is fx, over this distance, which is fc, and the angle direction is clockwise. So first, tan 2 theta p is fx over fc. How to get fx and fc? If you look at the figure, fx is equal to tau of the absolute value of tau of x, which is 30. Okay, and you have that fc. Once you determine the coordinates of c, the coordinate of c is plus 15, and the coordinate of f here is minus 60. Then the distance from F to C is 60 plus 15, it's 75. So tan 2 theta p is 30 over 75 equals to 0.4. Now you can say that 2 theta p is 21.8 degrees into clockwise direction. So on the figure of element, I should rotate from X to the principal axis an angle of 10.9 degrees. The importance of getting to theta p, you will see it now, because they asked you what will be the state of stress for if I take if I rotate the element through an angle first of 25 degrees clockwise. Keep in mind that if I rotate on the element 25 degrees clockwise, I should rotate on Mohr circle 2 times 25 degrees clockwise. So I should rotate 50 degrees clockwise from X. Okay, because here we have the orientation on this figure of reference are X and Y. So if I rotate 25 degrees clockwise here to get X prime, Y prime. So this is X prime. And this is Y prime. If I rotate here 25 degrees clockwise, as we said, we should rotate 50 degrees clockwise on Mohr circle. So going back to Mohr circle, this is my X orientation. From X, I should rotate towards X prime 50 degrees clockwise. But now to do my geometrical calculation, I should find the angle between Cx prime and the horizontal axis, which is sigma. So I need which angle now? I need this angle. And this angle can be calculated now because I determined what is 2 theta principal. So I can say that angle phi here between of rotation from the horizontal axis to X prime is simply phi equal to 50 degrees minus 2 theta p. And once I obtain what is phi, I can easily calculate what is sigma x prime and tau x prime. Because once you know this angle, you say this distance. So this point is of coordinates sigma x prime and minus tau x prime y prime. Okay, so this distance is equal to cx prime, the distance from cx prime, which is the radius of the circle. Okay, and the radius of the circle, I can calculate it by just saying that r equal to radical. This is the radius here, it's cx. The radius is the distance from c to x, and I already know what is fx and what is fc. So the radius of my circle is radical of fc squared plus fx squared, which were already determined. So I do radical 75 squared plus 30 squared, I get the radius. Now I use the radius because cx is equal to cx prime. I use the radius to calculate what is tau here, because this distance d is equal to r sine phi. Okay, and therefore, because the coordinate is minus tau xy prime y prime, so I can say that tau x prime y prime is negative, equal to minus r sine phi. So now I determined tau x prime y prime at this point. If I want to get sigma x prime is also negative, as you can see in the figure. And to get the value of sigma x prime represents which distance? When I project point x prime, this is sigma x prime. It's minus this distance. And this distance is the difference between the distance from C to this point, which is r cosine phi, minus this distance OC. The distance from O to C is 15. So you can say that sigma x prime is equal to minus the distance from O to F. From O, sorry, let us say the projection of this point. You can call it F prime if you want, this point F prime. Projection of x prime on the axis. So it's minus O F prime. It's equal to minus the distance from C to F prime minus OC. So sigma x prime is equal to minus this distance, as we said, is r cosine phi minus 15. The distance from O to C is 15 megapascal. Please pay attention for units. If you are using the distance from O to C in megapascal, the radius also should be expressed in megapascal. So keep here same unit for all of your stresses, normal and shear stress. So if you are dealing with megapascal, then your result for all points will be in megapascal. And now we determined the state at x prime. We still need just, once we have tau x prime y prime and sigma x prime, we still need sigma y prime. So this is point y prime. To get sigma of y prime, we should determine the distance from O. If we call this point, for example, let's say d prime. Okay, so the projection here, sigma y prime will represent the distance from O to this point. So we can say that sigma y prime is equal to this distance OC plus CD prime plus CD prime. OC is 15. We have seen already that OC is 15. And C prime, D prime, as you can see in the figure. Okay, let me show you. So this is D prime. You want now this distance from C to D prime. It's equal to, first, this angle here. Oh, sorry, just, we want, this is Y prime. We project Y prime. Okay. Y prime, this is F prime. You want to get this distance from C to F prime. So what you do is you say this is equal to the radius R. This angle here is opposite to phi, so this is also phi. This angle is phi, okay? So you can say that CF prime is R cosine phi, and I should add to it OC. So in total, sigma y prime is equal to OC plus R cosine of phi. And then you can get the value of sigma y prime, and you determined completely the state of stress for a rotation of angle of 50 degrees clockwise on Mohr circle. So on the element, you are rotating an angle of 25 degrees clockwise with respect to frame X. Now, for the second case, they want you to go over. They want you to find what if I rotate 10 degrees counterclockwise with respect to XY axis. If I rotate on the element, so this is X, this is Y. If on the element I rotate 10 degrees counterclockwise, so on Mohr circle, I should rotate 20 degrees counterclockwise. So this is X second and this is Y second. And I want to find the corresponding state of stress in this frame. So now I go back to my Mohr circle and I say, let me now rotate from X-axis an angle of 20 degrees into the counterclockwise direction. So this is my X-axis. I should rotate from it an angle 2 theta equal to 20. So this is 20 degrees. And now I want to determine what is the state of stress for axis X prime, Y prime. So I can just say that the coordinates of X prime are sigma X prime minus tau or X. If you want, because we named X prime, Y prime, you can say here X second, Y second if you want to differentiate. So sigma X second minus tau X second, Y second. And for this point here, it's sigma Y second plus tau X second, Y second. Now, to start with, same procedure. For this point, I need to determine the angle with the horizontal. And as you can see, I already know the angle 2 theta p. Okay? And now I know that I rotated a counterclockwise an angle of 20. So the total angle phi here is the value of 2 theta p we calculated before. So phi is 2 theta p. Of course, theta p measured in the clockwise direction, and the plus 2 theta, which is measured into the counterclockwise direction. Because look, from X, I rotated to the principal axis into clockwise direction in angle of 2 theta p, while from X to X second, I rotated into counterclockwise direction in angle of 20 degrees. So the total angle will be 2 theta p plus 20. And once I find phi, the value of phi, all I have to do is to say that if I project here and I call this point, if this is X second, I can call this point F second. And to get sigma is equal to minus the distance from O to F second. So sigma X second is equal to minus O F second. So it's equal to minus CF second minus OC. OC is 15. For CF second, I do the radius cosine phi. Okay, so it's equal to minus R cosine phi minus OC. So same expression if you want. What changed is just the value of phi. And I do the same to get sigma y second. Sigma y second will be plus OC plus R cosine phi. Okay, so this is for sigma x second and sigma y second. For tau, very simple. For tau, I say that this represents minus tau x second y second. So since I am in the negative tau, I can consider then that tau x second y second is positive, because minus tau second y second is negative. This means that tau x second y second is positive here and is equal to plus this distance, and this distance is r sine phi. So here you have positive tau x second y second, which is equal to plus r sine phi. Okay, so for each phi, depending on the value of phi, you might have negative or positive tau. If you look at this figure here, you have x prime was from the side of positive tau, so tau xy is negative because the coordinate of x prime is in shear is minus tau x prime y prime. And since here the coordinate was positive, then tau x prime y prime was negative. However, in the other case, you have from the other side x prime is, or x second is from the lower side. So since the coordinate of x prime is negative, this means that tau x prime y prime here is positive. So geometrically, we were able to find, as we said, the values of stresses for different orientations. Another problem. Now again, so if you remember, we solved these problems using direct application of the formulas. Now we'll solve same problems but using more circle. So here we have two members of uniform cross section of 50 times 80 millimeters that are glued together along plane AA that forms an angle of 25 degrees with the horizontal. Knowing that the allowable stresses for the glued joint are sigma equal 800 kilopascal and tau equal to 600 kilopascal, determines the largest centric load P that can be applied. So first, same procedure as we mentioned before. The first step will be to consider the plane XY, the normal plane XY. In the normal plane XY here, if you do a cut like this, relative to this orientation, if I take this is X and this is Y, I have only stress along, so if I take an element like this, I will have only stress along Y direction, normal stress along Y. I don't have along X and I don't have shear. So the state of stress is sigma X equals 0, tau XY equals 0, and sigma Y is plus because it's tension, P over A. Now, once I determine the state of stress in XY plane, I can draw the Mohr circle. And for the first point, coordinates will be sigma X minus tau XY, which is 0.00 here. So I can say that XY here represents the principal axis already, okay? And sigma Y is the coordinate of sigma Y, or sigma Y plus tau XY, so sigma Y is 0, and sigma Y is equal to P over A. So this is my points corresponding to the principal axis because shear is 0. And I have, once I put these 2 points, I can compute sigma average, and the radius then of my circle R is P over 2A. Now, if I go back to my figure, as we mentioned before, in the plane of interest where I have the glued joint, this is my section of interest, doing an angle of 25 degrees with the horizontal, okay? But as we mentioned, whenever we want to see the rotational angle, this is x, this is x, this is y. So if I look at my figure, okay, the angle of rotation I did is the following one. So this is now for this face. This is my faces. Okay, I have this axis. So if I call this x, this is x prime, let's say. This is y prime. You were interested into the state of stress for this face, this one. So we want to get sigma y prime and tau x prime y prime. Okay, so we were not, the question was just to calculate the state of stress here and not here. You can find sigma x prime, but what they want from you is sigma y prime, because this is the glued section. Okay, this is the glued section. So what you can do here, you can illustrate point x prime y prime on the Mohr circle, but it's enough to find sigma y prime and tau x prime y prime. No need to find sigma x prime. Okay, now as you can see here, we rotated from x to x prime an angle of 25 degrees into the clockwise direction, and we rotated from x to y prime an angle of 65 degrees into the counterclockwise direction. So if you just want to represent point y prime on your figure, okay, you can say, because I rotated from x axis an angle of 60 degrees towards axis y prime, then on Mohr circle I should rotate an angle of 130 degrees into the counterclockwise direction. Okay, so this is my origin. This is the center of my circle. I rotated from on the figure of element. I rotated from x axis towards y prime axis an angle of 65. So here I should rotate on Mohr circle an angle of 2 times 65 into the counterclockwise direction equal to 130 degrees. No need to illustrate point x prime because they only want the state of stress in the plane of glue, so which is perpendicular to y prime. So I just need to define this state. What is sigma y prime and what is tau x prime y prime? Okay. So now I can say that looking at my figure here, I want to determine these values. Sigma, I do the projection. Sigma of y prime represents this distance from the origin here till this point. This distance is the following. So geometrically, I have, this is 130 degrees, and I have the distance from C to X is equal to the radius of the circle. The radius of the circle, as we mentioned together, is sigma y over 2 is equal to P over 2A. Now, you have concerning the shear, as you can see here, this is y prime, this is axis y prime, and this is axis x prime. Okay, We have that for point, when we represent point y prime, the coordinates of point y prime are sigma y prime and tau x prime y prime. So since we have that point y prime is on the lower side here, this means that we have a negative tau on for this element. Tau x prime y prime is negative. Okay, and this is why they illustrated as sigma and minus tau. Here, tau represent for them the absolute value of shear, and it's in the negative direction. So if you represent it on this face, it should be negative. You know how to do this on face of normal parallel to y prime, because tau is negative, tau x prime y prime should be oriented along negative x prime. This is why they presented tau along this direction, because tau x prime y prime is negative. Okay, and they called it tau an absolute value, but it is already in the negative direction. So this point then will represent sigma y prime and tau x prime y prime, and tau x prime y prime is negative equal to minus tau, and sigma y prime is positive because you have sigma y prime is positive since you have it, since when you do the projection it is on the right side of the origin, so you have tension on this face. So now to determine your values of tau and sigma, you use geometrical methods. So first we said that this distance represents the radius, which is p over 2a. We should add to this distance the projection here, the projection of this point from the center towards this point. This distance is equal to the radius times cosine of this angle. So this distance is r cosine 50. So sigma at y prime is p over 2a times 1 plus cosine 50. And to determine tau, all you have to do is to get this distance. This distance is r sine 50. So the value of tau is